Alright, welcome back everybody. In this video we're going to look at the examples from the fluid force lesson. First off, we're going to look at this first example where we're finding the total force on a constant depth surface. And in order to find that, the force is equal to pressure times the area of the surface. And the pressure is determined by two factors. Number one, which is the weight density of the fluid. And number two, which is the depth of the fluid. And then this last characteristic here in determining the force is the area of the surface. So in our first example here, we're finding the force on the bottom of a cylindrical container that has a radius of 4 feet and a depth of 8 feet if it is completely filled with milk. So we've got a cylindrical container, and we're finding the force being exerted on this bottom surface. Okay? And what makes this problem easy is that bottom surface is always at a constant depth. So I've got force is equal to the weight density, which for milk is 64.5, times the depth of the surface. The depth of the liquid on the surface is 8 feet here, since the tank is 8 feet tall and it's completely filled. And then times the area of the surface. And the bottom surface here is a circle with a radius of 4. So the area of that surface is just going to be pi times 4 squared, or 16 pi. And so we can calculate the amount of force exerted on this surface. I'm just multiplying all of these together. 64.5 times 8 times 16 pi. And you get 25,936.989. If I read that correctly. Yep, 0.989. And our units for force here, realize that the units that we've got, the weight density is in pounds per cubic feet. The depth is measured in feet, and the area of the surface is measured in square feet. And so this works out to our units just being pounds. Okay, on to some more difficult examples. On this side, we're looking at what happens when we have a variable depth surface. Okay, the surface does not have constant depth. So we're going to, in order to find the fluid force, the weight density is going to be constant. We're going to integrate from the bottom of the surface to the top of the surface the depth of the typical strip times the area of the typical strip. Okay, so let's look at example 2. Here we're going to find the force on the side wall of the same cylindrical tank, still filled with milk completely. The radius of the tank is still 4 feet. The height of the tank is still 8 feet. And we have fluid all throughout that tank. So let's set this up. We need to set up a coordinate gridding system, and we can either establish h equals 0 at the bottom of the surface or at the top. And sometimes you use a little judgment. Sometimes it's easier to set it up so that you're using h equals 0 at the bottom. Sometimes it's easier at the top. Sometimes you just establish a system and then develop your model based off of that system, and you're good to go. So here I'm going to set it up so that h equals 0 at the bottom and h equals 8 at the top. Our weight density of our fluid is 64.5. And now we're finding the force on the side wall. And so we've got the depth of the liquid. We're integrating from the bottom of the liquid to the top of the liquid. And the depth at any particular point is 8 minus where that particular piece is. For instance, the strip that we're going to look at the very bottom of the tank is at a depth of 8, which is why I made this 8 minus h, because when we're at height 0, the depth of liquid there is going to be 8. And now I need the expression for the area of a typical strip. Now realize the strip that we have on the tank on the side, we've got this circular piece. But the area of the strip, we're going to actually unroll that circle, and its thickness is going to be dh, but the width of the strip is going to be the circumference of one of these circular pieces. So it's going to be 2 pi r, so 2 pi times 8, pardon me, 2 pi times 4, got ahead of myself there, and so that's going to be 8 pi. And if I wanted to, I could bring that out in front of the integral, but since I'm just going to calculate it on my calculator anyway, I'm just going to go ahead and do that calculation. So let's pull up our calculator, and we've got 64.5 times, and you know what, I'll bring the 8 pi out in front of the integral, times the integral of 8 minus h in terms of h from 0 to 8. And you get 51,873.978 pounds is the amount of force on the side wall of the tank. Okay, let's look at example 3. A metal plate is submerged in a tank of water with weight density of 62.4 pounds per cubic foot, as shown in the diagram below. Find the force on one side of the plate. Okay, so I'm going to establish my coordinate grid system. I'm going to call this h equals 0, and this h equals 12 at the surface of the water, and start setting up my model. My weight density is 62.4. I'm going to integrate from the bottom of the surface to the top of the surface. The surface is 8 feet high, so the top of here is at h equals 8. I'm going to integrate from 0 to 8. Then I need the depth of a typical strip. So if I draw in a typical strip here, how deep into the water is it? And that's going to be 12 minus h. Since the water is 12 units deep, the very bottom of the tank here at h equals 0 is 12 feet deep. The very top here at h equals 8 is 4 feet deep. So we've established our depth based off of that. And then we need the area of the typical strip. Now, these widths of the strips vary depending on the value of h. When h is 0, the width of the strip is 0. And when h is 8, the width of the strip is 6. And so we can come up with a formula here for the width of the strip based off of the depth or the height of the strip in the water. So let's see, we've got h is to w as 8 is to 6. And if we solve this, h is 4/3 w, so w is equal to 3/4 the height. And so the area of this strip, the width of it is 3/4 the height. The thickness is the change in height. And so our model for the area of a typical strip is going to be 3/4 h dh. Now I have my model set up, and I'm going to go ahead and calculate the force, 62.4 times the integral, the quantity 12 minus h times 3/4 h with respect to x from 0 to 8. And we get the force that's exerted on this particular metal plate on one side. Okay? So in conclusion, when we have variable depth surfaces that we're looking at, there are several key characteristics that we need to look at to set up our integral. We need the weight density of the fluid. you see right here. We need the location of the bottom and the top of the surface based off of our coordinate grid. We need the depth of the surface based off of how far a typical strip is from the surface of the fluid. And then we need the width of a typical strip, or the area of a typical strip, which we find by using whatever area formula is appropriate in a given context. In this case, we were just cutting a slice out of this, and so it was a rectangular slice where we needed the width and the height of the strip. And once we do all that, we set up our model and go. Alright, that's the end of this video with the examples on fluid force. See you guys next time. Hope you have a great rest of your day.